Okay, spring 2011, number 10, optimization problem. We have a cylindrical barrel. It has a volume of 32 pi. The pi is included. And so that's a constraint, that the volume is equal to 32 pi. The volume of any cylinder is pi r squared h. So that 32 pi is equal to pi r squared h. And we'd have the pi's canceling out. And we'll call it h being equal to 32 over r squared. Okay. Great. What are we trying to maximize? That should be a R4. We're trying to minimize cost. We have cost for the top and bottom being $6 per square foot. We take that and multiply by square feet. For area, we have area of the top and bottom, and that's going to be pi r squared h, two of them, I'm sorry, pi r squared, two of those. Sorry, I put an h in there by accident. Sorry. Yep, two of those pi r squares. That'll be the top and bottom area, $6 per square foot. That'll be the cost in dollars. When you take the side, the lateral area, what happens is, think of it as like a label on a can, slice it, and then unroll it, and you'll actually end up with a rectangle. Now, unrolling it will give you a length of the circumference, 2 pi r. The height will still be h. So the area for the lateral side is 2 pi r h. And that cost $3 per square foot. Multiply that by 2 pi r h. And that will be our cost equation, simplifying to be 12 pi r squared plus 6 pi r h. Knowing that h is 32 over r squared, we get 12 pi r squared if we multiply by 32 over r squared, that'll give us 32 over r, but then times the 6. 192? Yeah. So C is 12 pi r squared plus 192 pi over r. I'm going to take the derivative of that. We get 24 pi r minus 192 pi over r squared. And we're going to set that equal to 0. so that we get 192 pi over r squared equals to 24 pi r. Pi's cancel out again, and we'll have r cubed is 192 over 24. And I think that's 8. So think of us as multiplying and then dividing, multiplying by r squared and dividing by 24 both sides. Ending up with r cubed is equal to 8 conveniently, so r is 2. They don't want the r, they want the height. And if r is 2, then h is 32 over 4. So h is 8. We haven't proved that we have minimized cost. We just proved that we have the derivative equal to 0. So for the last 2 points, 8 out of 10 total right now. So for the last 2 points, we take the second derivative. Take a look at that. Second derivative would be 24 pi minus, no, plus, let's see, doubling 192. 384. Double check me on that, but I think it's, yeah, I think it's right. So that we get, yeah, this is your second derivative. No matter what, positive r would always be greater than 0 for r's that are positive. And so, yeah, second derivative always positive means to you that the function is always concave down. So this local minimum that we have found turns out to be the absolute minimum. And that's the 2-point argument using the second derivative. You could also do the 2-point argument using the smallest and largest r could be. I do believe that r should not go too far. R definitely could be 0 on the low end, and then r can't be too large. That would then in turn make h very small. So you could come up with something on the high end of what r could be. Plug those back into your cost equation. Seems to be a bit too much work though. So let's just keep with this argument. Sounds good.